Alright, so I think this is recording. We're taking a look at the graphs of logarithms, trying to get used to the different properties of these log functions. They are the inverse of an exponential. The domain and range of inverses have switched, so the range of any log function is always all real numbers. So I can answer that immediately anytime I see it's a log function. Now, the domain for a basic log function is 0 to infinity, but this plus 2 has shifted the graph. And remember, shifts, when you're adding or subtracting to the x-coordinate, it's kind of bizarre in its behavior. You're not actually adding to, you're subtracting to when you think of how the graph shifts. So it shifts to the left 2 units, and my domain is from -2 to positive infinity. Since there's been no reflection across the y-axis, this -2, I can also state that, hey, that's my vertical asymptote. So let's sketch this real quick. We've got this log function. There's been no stretches or no shrinks. There has been a shift to the left. That's the only transformation that we have, a shift to the left 2 units. So where this graph used to get closer and closer to the y-axis, it's now going to get closer and closer to the line x equals -2. What used to be an x-intercept of 1 has now also shifted to the left 2 units, and we'll see 1, 2, that I can prove to you algebraically that my graph is crossing the x-axis at -1, and that it looks like this. Alright, so this is the x-axis, that's the y-axis. So here was a visual way to shifting the graph left 2 units to get this x-intercept of -1, but let's get it algebraically. Alright, so I'm going to come in and delete my sketch of my graph just to give me more room to work with an equation. If you're on the x-axis, then the y-coordinate is 0. And the y-coordinate is the output of this function. So if I set the output of this function equal to 0, and I solve this equation, it will give me the x-intercept. So this equation is currently in logarithmic form. And I really can't get the x by itself because this isn't log times this. A log isn't multiplication, it's a function. About the only thing I can do is change the form of this equation and to change it from log form to exponential form. So let's start with the base. The base for a logarithmic function is always this small number that's by the g there. If it's not there, then it's a common logarithm and a 10 is implied. And if instead of log, log, they write ln for a natural log, the base would be e. But for us, for this problem, the base is 4. Now, this 4 is going to have an exponent associated with it. And from the equation, the logarithm equals the exponent. Since this log is equaling 0, then 0 is my exponent. The argument of this log function is x plus 2. So that's what 4 raised to the 0 power is. By definition of my properties of exponents, 4 to the 0 power by definition is 1. So if I subtract 2, x has to be a -1, and that's what we were expecting. We knew from when it shifted to the left 2 units that the old x-intercept at 1, 0 shifted to the left 2 units and has coordinates of -1, 0. So here we confirmed that algebraically. Hope that helps, and I'll talk to you later.